The next talk of this morning is by Gigliola Staffilani, and I was told to read this title. So it is on random versus deterministic approach in the study of wave and dispersive equations.
So first of all, thank you to the organizer for the invitation. And then sorry for, maybe you thought that my talk would be a mix of math and behavioral sciences, since there was something about being determinate, but actually just about math. So. And then I want to talk briefly about when I first met Sergiu. I think that's probably 20 years ago, something like that, when I first arrived in Princeton. And I have to say that Sergiu was certainly the first, beside Carlos, of course, and Jean at the IIS was the first big shot person I interacted with. And although it was very intimidating at the beginning, I have to say that Sergiu has been extremely supportive all the time. And then last thing I want to add is that this is a comment that probably men are not supposed to make about women, but women can make about men. So really, Sergiu didn't change at all. So I don't know how you do it. Maybe you have a portrait somewhere that is aging, but certainly you are not. So we're going to have a conference again in 20 years, okay? Okay, so now to the math. This is a talk a little bit different than what we have been hearing so far, and because in the last few years I have been collaborating, especially with Andrea Nahmod, in problems that introduce a little bit of probability in it, but very little. So this is the randomness. So let me give you an outline of the talk. So we'll have some general introduction, and I will talk a little bit about what is the randomness component in this business, in particular what we mean with random data. And basically this is the main reason why things work. So we have this very nice large deviation type estimates that we will apply over and over again. And I will give you a very simple example of why by taking random data, we are able to solve some problems that have even counterexample if you do it in a deterministic way. And at the end, hopefully I have time, I listed 3 problems. 2 of them are very similar, and they are about the nonlinear Schrödinger. But the last one, it's more relevant for this audience because is more on the wave equation and more on geometric flavor, and in particular there is a null form condition in there. And I will try to explain how even in this context of randomized initial data, the null form condition actually plays a role. Okay, so we all know that in the last, 20 years there has been an incredible progress that has been made in the study of wave and dispersive equations, and this is from a deterministic point of view. And what I mean with that is, like, I give you an initial data I take a set of initial data, usually a certain space, subwhole space, or whatever else, and then you want to prove something for all those elements in the set. But still, in spite of the great progress, there are several open questions, open questions that become more and more difficult. As we know, when we start working on a field, and then after 20 years, the very hard questions remain. And I wanted to illustrate a little bit some of them. And as an example, I just picked here the nonlinear Schrödinger with p-order nonlinearity, but you can say something similar to what I'm going to say here also for wave equations and so on. So let me just use this just for the sake of time. Now, one important, as we saw, by the way, in the beautiful story that Igor told us yesterday, there are several things that you can understand from the beginning about the problem just by looking at the scaling, if the problem has a scaling. So let me do the same here. So I take SC to be the critical scaling, which depends, on of course, on the dimension. It depends also on the order nonlinearity. And if we take S above this critical scaling, then we are in a regime which is called supercritical, really hard. If we are at this critical scaling, it is hard, but there are results nowadays. And if we are below, pretty much we consider that a more classical theory. Okay, so let me briefly go through, at least for the problem that I mentioned. I'm not going to talk about waves. In this case, it's about the Schrödinger. Let me just give you a little bit of where we are at the moment. So I'm taking critical, I'm in the critical situation. So that's the one in which the scaling doesn't help because it's not going to make anything small. So you really have to look at the problem in the global sense. And if we are looking for global results, global well poses, then the picture looks pretty good at the moment, at least for the problem that I gave you. And here, this slide here, I'm not going to go through all the names, but I would like to put some of them. This is for Rn. So we are in the nicest manifold Rn, so nothing curved. And there are results that you can see here. Now, in the supercritical situation, the situation is much less understood. So I put there like a nice question mark, which is a lot to do. And then the next slides, it's about changing your domain from the flat Rn to an example of a compact manifold that's the torus of dimension n. Yesterday, Jean talked as a consequence of the decoupling conjecture. He mentioned the proof of the Strickhart's estimates on irrational tori. So from that, you probably gather that thinking of a rational torus, and for rational torus, what I mean is that let's take, for example, dimension 2, the ratio between the two periods of the torus is a rational number. So if it's irrational, the situation is much more complicated in terms of finding Strickhart's, and in fact, this was solved as a consequence of the decoupling conjecture. Anyway, this is just to tell you that when I talk about torus, if I have to distinguish between rational and irrational, I will do that. If I don't distinguish, you can assume that it's for everything. Although you understand that the situation might be quite harder if it's irrational. Okay, so in terms of global well-posedness in the torus, you see there is a lot less. That's because the problem is a lot harder. And here I want to mention just the global result in 3D from UNESCO and Posador based on some previous work. And if we are going lower, like if the critical norm, instead of being the H1 norm, is the L2 norm, so we are in the situation in which the mass is the critical object, then there is nothing at that level, really. So let me move on and consider, in fact, the situation when we are close, at least, to the mass critical problem. So this is a result of Bregan, and it's the result that I want to present because it's a nice bridge between the deterministic and the random approach to these problems. So let me move on. So actually, let me go back. So this that I'm looking at here is the 2D, so we are in the torus of dimension 2, and then I have a cubic nonlinearity. Now, this kind of equations in the realm that I will address in a moment, which is this context in which we're going to use random data, is not a good equation. You have to, we say, weak order it. So what that means is to subtract this quantity. Now, this might look strange to you, say, why do we do that? And from my point of view, and for the application of the concept that come from probability, the reason why you do this subtraction is because when you look at this nonlinearity in terms of Fourier, in the Fourier space, you need to remove certain frequencies. You cannot allow that certain frequencies are equal to each other. And I will explain you why in a second. So let's now change the problem that we had at the beginning, which is the blue one, and let's add or subtract this green part, and then now we call this equation weak ordered. This is, in fact, it's called like that because this nonlinearity is attached to a certain Hamiltonian, and really what you do is you weak order the Hamiltonian, and then this is the consequence that you get. Anyway, so take our initial data, which is U0, and here, in fact, I have to make a distinction. I believe the theorem is proved for rational tori, and I'm not sure the proof goes through for irrational, meaning that you will need to use not just Strickhart's estimate on irrational tori, but also other estimates which are similar to Strickhart's, which in the case of Bregan, for the rational one, are consequent of certain counting on the lattices, but which I'm not sure they are true yet. So we'll keep the in parentheses here that we are considered a rational torus. And so what it proves is the following. I said there is no result at the level when you say that if I'm assuming initial data is in L2, then do I have a solution? We do not know that. But what we know is the following. So that this problem here, this initial value problem, is almost surely globally well posed below L2. That is in the supercritical. So I have to explain what all of these words means. And so let me go to the next. So a very informal definition of almost sure well-posedness is the following. So first you need a measure, a probability measure. The probability measure is set up in the set of the initial data. Okay, so once you have a probability measure on a space of initial data, which here in general I'm going to call it X, and in the next few examples will be Sobolev space, but that's not necessarily always true. Then we say that the problem is almost surely well posed, whether local or global depends, but is almost surely well posed if there is a set Y, which is a subset of X, a full measure, that's what is important, full measure, and such that for any initial data on this Y, there exists a certain time and a unique solution U for the initial value problem at hand, in this case it would be this guy, that it's continuous with respect to time into X, and so on and so forth. So everything is the same as the usual definition of well-posed, except that it's almost surely if we have a set Y, which is full measure for which you can actually talk about the evolution. Okay. Now, I wanted to remark that this problem here, we knew deterministically that was at least locally well posed whenever you are in HS for X strictly greater than 0. So the L2, which is the mass, is not really part of that. All right, so let me explain a little bit more this work of Bregan. So I believe, and I actually never talked to Jean about that really what he wanted to exploit was the idea of invariant measure. And this idea of invariant measure is very simply understood when you have a Hamiltonian system which is finite dimension. But the problem that I just wrote before, the NLS, cubic NLS, you can view it as an infinite dimension Hamiltonian system. So it makes sense to think about invariant measures on this infinite dimensional Hamiltonian system. So the work in terms of defining a measure on this kind of system was already present in the literature before Bregan's work. It was Leibovitz, Rosenspiel, and Zitkov and so on, but they only defined the measure. Whether this measure was invariant or not was not proven, and the reason why it was not proven is because there was not even a global flow. So if you don't have a flow in the support of the measure, it doesn't make any sense to talk about being invariant, right? So Bregan in his work not just proved the existence of the flow, he was able at the same time proving the existence of the flow and the invariance, and then use the invariance of the measure to make the flow global. So the invariance of the measure was used in place of conservation laws. There is no conservation law below L2, at least that we know of. And so this play of the two things together, and so at the end, he obtained not just the existence of a global solution almost surely, but also the invariant of a measure that was already defined by Leibovitz, Rosenspiel, and Zitkov. Okay, so more precisely, let me read here. So he established local well-posedness in the typical element of the support of this measure. I'm not going to go through the measure. I'm not going to tell what that is. It will take me too long. But that's what it did. And the typical element, I will write for you what is the typical element in the support of this measure. But what you need to know at the moment is that this typical element belongs to the H minus epsilon space in T2. And this is a supercritical space for the equation that I wrote before in the sense that I explained at the beginning. Now, this, the measure that it's invariant, okay, usually is defined as the Gibbs measure, and this part is really the part that, in a sense, it's more new for people working in dispersive equations. And I'm going to tell you what are the limitations and so on in a moment. Let me give you the idea of the proof. Like, I'm not going to do much computation except one specific example where I wanted to show you why randomness is important. But the idea is the following. So you want to look for the solution of u, the equation, but instead of looking for that, you take u minus the linear evolution of your initial data. It turns out that this w, which is the difference of these two guys, is actually smoother than the initial data itself. And what you end up proving is that this w satisfies a certain difference equation that in a way it's a combination of a deterministic, that you approach in a deterministic way, but there is some randomness in it as well. I wanted to point out though that the result of Bregan is only at h minus epsilon. You cannot extend it. There is in other words, there is no such a thing as preservation of regularity. Okay, so if you know h minus epsilon, you don't know what happens later on. So the question of the global well-posedness for s between 0 and 1 was remain open. You cannot extend. I will go, this is one of the problems that I wanted to present, so I'm going to talk about this more later. Okay, so what is this random data? Okay, so the typical element in the set where you define these measures, these Gibbs measures, look like this. So this is the Fourier coefficient. You are reconstructing with the Fourier, the basis in your Fourier space. And you define phi omega. Omega tells you that I'm talking about random stuff in this way. Now, Gn omega, that's the, an important new variable here in this jobs. And so these are independent identical distributed standard, in this case complex, because we are doing NLS, but later on when I move to the wave, it's going to be real. Random variables on a certain probability space. You can forget about the probability space in what comes next, but this is how it is defined. Okay. Now, one remark to make, which is actually important, is that if we compare phi omega with this phi, where I remove the random term, so this is not random, this is random, these two guys are in the same space in terms of regularity. In other words, doing this randomization here, putting this, if you like, plus or minus 1 randomly, is not improving the regularity of this object in terms of derivatives. Okay, that's not happening. So if I was in h minus epsilon and I randomize, I'm still in h minus epsilon. I don't make the object better. But there is some other kind of regularization that happens, and that's what I wanted to exploit in a moment. So the kind of regularization that happens by taking this random initial data, it goes back in history and can be already found, obviously, in some of the classical harmonic analysis. So let's look for, as an example, about the Rademacher series. So call f omega, this is the sum, n 0 to infinity of an Rn omega. Omega is now in the circle. An is a complex number, and Rn omega is the signum of the sign. Now, there is a classical theorem that says the following. If you have an in little L2, this object f omega is also, is well defined in L2, so no problem with that. But what's more is that f omega belongs to LP almost surely, and in fact, there is this kind of inequality. So what you did by introducing this Rn omega is to increase the LP regularity of the function itself. Now, this is not what you use when you have to do the estimates in Bregan's work. This is too simplistic to use. So I want to give you an example. What is that you use in that context? Okay. So in order to do that, let me introduce this particular large deviation type estimate. And again, Gn are these random variables that I introduced before. And f omega is now the sum of Cn and Gn omega. And what you can prove is that if you look at the LQ norm of that, you have this estimate. This is closer to what I showed you about the Rademacher series. But what is more important somehow for us later, what's going to be more important, is the following fact. When you do estimate, you're really worried when things become really big. Okay? So you would like to have a control in the size of objects. And this is what we can say. So if I have an expression f omega like this guy here, and I'm wondering when is or what is the probability that this expression is larger than a certain lambda, then I know from here, and by using Chebyshev inequality, that the probability such that the size of f omega is greater than lambda is exponentially small. So it's the exponential of minus, the minus here is fundamental, c lambda square over this L2 norm, okay? Now, I would like to have an expression of this which is more multilinear. This is not a multilinear expression. It's just one object, and I'm telling you what happens. So let me give you a version of that which is more multilinear. So in particular now, let's define fk omega to be this big sum. So now I have many terms, many random variables, and this is the coefficient, Cn1 all the way to nk. And I'm summing over a certain set of, if you think of this in frequencies, set of frequencies. And there is an equivalent estimate that we had before. In other words, fk of Lp is less or equal, this of course depends on k and p, but the point is that you have the L2 norm on the other side. And again, by using Chebyshev inequality, the same as before, if you have this large, long multilinear expression, and you wanted to understand when is big than a certain quantity, then you know that the probability when that happens is small, and is in those terms. So that's the game that we're going to play. If we cannot control certain terms, what we're going to do is we're going to remove the amount of the omegas where the set is the expression is too big, but that set is not going to be too big. So that's the idea. And so what we have, by the way, I wanted to mention that there is a very nice explanation of all this in the language that maybe people in dispersive equation are more familiar with, in some work of Tsetkov and Toman and Tsetkov, so they actually write really well in this context. Okay, so at the end of the day, what it's used in the, certainly in the work of Bregan and the work that came later when he used the Schrödinger equation is the following. So give me a delta greater than 0. The large deviation result that I just mentioned above tells us the following. If you pick this particular lambda to be, in fact, the L2 norm and delta to the minus k over 2, then you have that in a set omega delta, which is smaller than the one you started with, but it's a good, I mean, it's a big size in the sense that its complement is smaller e to the 1 minus delta. So we can replace this absolute value by the L2 norm. And then you say, what's the gain by replacing the absolute value of an object with the L2 norm of an object? So I'm going to tell you what the gain in a simple example. So let's go back to the initial data that you use when you wanted to prove the almost sure well-posedness of the cubic NLS in the Bregan's work. This is the object. This is the object that the typical object that lives in the support of the measure. So that's what it wants to evolve. Now, you do your Fourier analysis so on, and at some point, when you have to estimate the nonlinearity, which remember is the cubic minus the mass times u, you end up having to estimate this quantity where f3 omega is this guy. Okay, so you need some explanation. So remember that I said that instead of solving for u, you're going to take u minus the linear evolution of the initial data. Now, if you imagine the difference equation that this difference satisfies, the w, you will see that in the nonlinearity, there's going to be a cubic piece, which is purely random, which is made by the evolution of this guy. So you have st of phi omega in a cubic expression. Now, if you look at that from in the Fourier space, and you do your convolution, so you write the Fourier space, you write the Fourier transform of the linear evolution, which you know lives on a parabola, and you put things together, you end up in writing this quantity here. So what is this? This is basically the convolution of 3 linear evolution of this guy. And why is it written like this on this set here? Well, let's think for a moment. So this is the initial, these are exactly the same initial data. And when you do the convolution, you sum them, you sum the n's and so on. So the set where you sum are n1 minus n2 and 3 equals n. So this tells me that I'm doing the convolution of 3 pieces, and one of them is with a bar. That's exactly the nonlinearity of the cubic NLS. So this is just because I'm doing the convolution of the 3 pieces. Now, the fact that here I'm restricting on n1 and n3 no equals n2 is exactly what the weak ordering tells me. It tells me that if I weak order the Hamiltonian or the nonlinearity, I remove certain frequencies. So now n1 and n3, so the ones without the bar are different than the one with the bar. And then this last constraint is because these are linear solution of the Schrödinger, so you know that they live in the parabola, I'm doing the convolution, and so that's what I get. Okay, but you have to trust me that a piece like this is what you have to estimate. So now let's do the naive estimate. So what do? Well, we feel like we don't really have much to do, so let's do a Cauchy-Schwarz. And in doing that, so I want to put the square inside, but in doing that, I'm going to lose the size of the set SM, which I wrote down below for you, the size of this set. Now, of course, when you start counting lattice points, you're going to, you have certain size. Okay, you restrict on certain balls, but you still, you understand that you lose, the size might be big, and then what that translates to in the world of Fourier setting is loss of regularity. You lose a derivative. You lose whatever amount of derivative this size here tells you. So that's not very good. So now let's do something smarter. So we use the large deviation estimates. I'm going to pick lambda to be delta inverse of this F3, where F3 is this quantity that I wrote before. And then I know by using this large deviation estimate that in the set omega delta, which is a pretty large measure, maybe it's not a measure 1, but it's 1 minus something small, one has that this norm here, which is written like that, is bounded by delta square, and then what I'm doing is what I told you that didn't look very promising, but was the bound of the L infinity norm with the L2 norm in omega. Okay, so that's what I did. I replaced the L infinity with the L2 in omega. Okay, now write the L2 in omega, which is this guy here. So this is one term, the first piece, and this is the conjugate of that. That's how you write the L2, is a GG bar. And now remember that you're doing the sum in this object here. And remember that some of the frequencies are not equal to the others. So in particular, N1 and N3 are not equal to N2, and N1 prime and N3 prime are not equal to N2. What does this translate into? Into the fact that because these G's are independent, everything collapses unless you have that N1 is equal to N1 prime and N2 is equal to 2 prime and so on. So everything dies out because the independence of the G's, except for what I told you, those frequencies are the same. If we had not removed those frequencies here, if we had not done the weak ordering, you could not have concluded this. Okay, so now let's stare for a second at what we had with the naive way and what we have with the randomization exploiting the independence. And you see that what we gain is exactly, or what we don't lose is exactly the derivative through the measure of that set. So in a nutshell, this is really what's going on. Of course, everything is much more complicated than this, but that's the idea. Okay, now, of course, in Bregan's work, it was fundamental, the idea of invariance of the measure. So that's itself a very important concept. But the question is, can we use randomization even though we don't have a measure? Okay, that because we are situations which we cannot define the measure. I will tell you a little bit more about why is that. And the truth of the matter is that yes, this randomization, exactly because that independence that I showed you before, it can be used in other contexts. So, so let me tell you how you randomize things. And before I randomized that typical element of the set of that measure that I was interested in. But in general, if you start with a certain function, which you can write like this, where HNX is your countable basis, in which you write, if you like, e to the I nx in the case of the torus, but if you have another manifold which is compact and you have a countable basis, you can do the same. So you start with this representation, and then what you do, you just randomize the initial data by sticking in this Gn omega, which are independent random variables. Now you can do that also in RD in the following sense. So if you start with a function phi, you can randomize it by randomizes the dyadic blocks in a sense. Well, they're not dyadic actually, because this is Pn phi, so this Pn is the projection operator on cube size 1 in frequency space. So you can randomize, and you can use the properties that I gave you before, coming from the large deviation and the independence of this variable. And the procedure, forgetting about the measure, of course, the procedure is the same. You expect that when you evolve in a linear way, whatever your problem might be, whether wave or Schrödinger or whatever else, Navier-Stokes, with some work in Navier-Stokes as well. So when you evolve the linear randomized data, let's call it V omega, and you take U minus that linear evolution, then the W is increased regularity, has a better regularity. And what it solves is some kind of a hybrid problem between an hybrid equation that has something which is totally deterministic, something which is totally random, and something which is in between. Okay. Now, with this randomization of the initial data, you can certainly hope to get local result below the usual threshold. So that can be done. Then the question is, how can you go from local to global? I gave you an example with Bregan's result of using the invariance of the measure. But there are restrictions on how much you can push that. And one of the main reasons is that, unfortunately, the regularity of the support of these measures decrease as you go up in dimension. And the kind of multilinear estimates that you have to do need to be done in smoother and smoother space. So you're kind of going farther away from what you can do. And the cubic in 2D is exactly the sweet point in which you still have a pretty rough set of initial data, but the nonlinear estimate can be still done there. In higher dimension, this does not happen, except in some cases you can use some assume radial, make some radial assumption. If you reduce it that way, the dimension of the problem. So the Gibbs measure has this kind of restrictions in order to be used to claim a global result. But sometimes you can also use, to go from local to global, you can use energy methods. So here I recall some people that use that in the case of the wave, and we use that in the case of the Navier-Stokes with Namod and Pavlovich. Sometimes you can use instead the argument that Bregan introduced in a deterministic setting, which is high-low frequency. But people know about that. You know what I'm talking about, but I'm not going to describe here. And here are the people that wrote that. And all these methods have limitations, but that's what people have been using. Okay, now, sorry, I want to do the whole thing to be fair, and also to claim that it's a very active field of research, this investigation on randomization and the invariant measure and so on and so forth. I put in this slide a bunch of names and the various equations in which this kind of arguments like the one I present are used. I want to disclaim, though, that the result, for example, the result of, where is that? Okay, wave, here. The result of Burke and Setkov, which is for a wave for which the right-hand side is just a power, so u to the p, okay? This kind of result is proved in a softer way than the kind of argument that I presented to you briefly about the independence of the random variable. And that's because the Schrödinger equation is, does not regularize the nonlinearity. When you write down the fixed point, if you have a wave, you know that the non-homogeneous term is going to be regularized somehow. And so that helps, while for the Schrödinger does not happen. So it's a softer argument in here. Later on, towards the end of the talk, I will present a situation which it's a wave equation coming from a geometric problem in which the right-hand side is still just having powers of u as also derivatives. Then in that case, the softer argument of Burke and Setkov does not work, and you have to use the kind of argument that I show you that Bregan used for the Schrödinger. But I'm going to go back to that in a moment. Okay, so here to sum up, whenever you have in a deterministic setting situations in which you really cannot move on, either there are counterexamples, certain multilinear estimates, or you are you don't have any more conservation law that you can use and so on, maybe it's a good idea to try to see if you can push through some of this concept that I show you now. So, oops, sorry. So what I want to, that typical example is supercritical regime, when certain type of ill-posedness is present, and when there is still some gaps between what to fill up the, like in the example of the NLS, when I say H minus epsilon because Bregan used the invariant measure, but you don't know what happens above that. So there are still gaps in there in terms of global existence. Okay, so now let me present 3 problems to show you a little bit what you can do with these techniques that I showed you. These 2 are very similar, and they address exactly the question of the gap. And the first one is almost sure global ill-posedness for 2D cubic. That's exactly the problem of Bregan. But now I'm in HS between 0 and 1. Remember, Bregan only consider H minus epsilon. You cannot push that through, just because, and I explain you why. The second problem is very similar. It deals with 1D, but it's of the similar nature, and most likely I don't have time to go through that, so I will skip that part. And then the last one is the one that I think it fits better Sergiu's taste, I guess. And this considers a 2D wave constant mean curvature, and it's a joint work with Magda Chubak and Diana Manderson and Andrea and myself. So it's one of the rare occasions in which there is a team of all women, so we'll see. Okay, so the first result, as I mentioned before, this dot here, hopefully you can see, this green dot here is the result of Bregan. So almost surely here, you have global solutions, and this is at the level of H minus epsilon. Then at 0, we don't know anything, okay, just exactly at L2, the problem is open. But if you are just above L2, so HS greater than 0, then we have a local ill-posedness. Now, if you're looking at from H1 on, because I'm looking at the defocusing problem and I have a Hamiltonian preserved, and this level you are subcritical, then you can use iteration to make a local result to global. And so this part, it's easy from the log, from H1 on, it's just an iteration argument from the conservation law. But we still can push the global ill-posedness a little bit below that, in fact 2/3, and that's done with the I method. So that's the situation. We know global ill-posedness deterministic way from 2/3 up. We know the global ill-posedness almost surely at this dot here, that's the work of Bregan, but we don't know what happens at this point. So the result S greater than 2/3 is due partially to Bregan, and then the Silva, Pavlovich, myself, and Sirakis. Now, why is this like a good problem to work on? Well, the point is the following. If you have a data here, you cannot claim that data is seen by the measure that lives down below at the level of H minus epsilon. So the theorem is non-trivial since this set sigma, which is in HS for S greater than 0, if you measure it, any set sigma which is in HS S greater than 0, if you measure with respect to the measure which is here, it's nothing. So in other words, you cannot claim that any of the elements here is in the set for which Bregan can claim that there is a global solution. So you don't even know that the solution can be continued in a lower regularity, which is something trivial if you are doing things deterministically. Okay, so briefly I'm going to go through the idea of the proof. So this is the typical element that we use, just like in the case of Bregan, the typical element that we use for for our well-posedness. And let me also warn you that at this level, there is no invariant measure that we can use. So the invariant measure only exists down on the H minus epsilon of Bregan. So this is the, so if alpha is equal to 0, then we go back to the work of Bregan, but if alpha is greater than 0, then we have something new. And so in order to prove it briefly, this is what we do. So I'm going to take a frequency capital N. I'm going to split this initial data into two parts. One part, n less than n, is W, which is smooth, very smooth. And this one here is another guy that I will try to compare with one of the elements that Bregan used. And that's exactly what happens is we're going to use some kind of comparison. So this an is 0 if n is less than capital N, and 1 over n alpha if n is greater than capital N. And then I'm going to define another initial data, which looks a lot more like the kind of initial data Bregan works with. So this guy here is exactly the kind of initial data Bregan works with. And this beta n now is a constant. It's not changing with respect to n. And this is smooth, so that's fine. Whenever you attach anything smoother to an initial data of Bregan, you're fine. And now I can certainly evolve that using Bregan's argument in a certain set omega n right here, which follows from the argument of Bregan. Now, I would like to find a set omega which works for anything, for all this n here. So what I do, I intersect. If this was on measure 1, the intersection you can do on measure 1, so that you can prove that, you can do that. And once you evolve that object, you get Vn for all n, once you restrict yourself on that set. Then what you do is you compare Vn with the object that you want, and there is a certainly different equation. There are some things that you can make small, and the comparison works. So anyway, this is the way you do, that you prove that there is at least a solution which is of lower regularity. And then you have to recover the regularity, but again, you can do that by using the idea of the proof of Bregan. Right, so now I have 5 minutes, I guess.
Oh, yes, sir.
Oh, yeah, I was looking at the seconds, perfect. Okay, so I don't even have to rush that much. I was looking at the seconds, they went pretty fast. So. Okay. All right, so the second example. So this is the focusing 1D quintic NLS. And the kind of problem is the same as the one I just showed to you for 2D. With small mass, this is something that you have to assume in order to define at the level of H1/2 minus the invariant measure. And, but it's a technical thing. I'm not going to go through that, but that just said that the mass has, not even small, has to be smaller than a certain quantity that depends on pi, which now I don't remember. So then I want to prove that there is almost surely global well pose in HS for S greater than 1/2. At the level 1/2 minus, Bregan had used an argument which is less sophisticated than 2D, because we are in 1D, obviously, but very similar to that. So what was known? So the deterministic method focusing and defocusing gives us the local well posing for S strictly greater than 0, okay? But that's just locally. The defocusing case, global well posing for S greater than 4/9, again, this is done by a combination of, if it's defocusing, you can use the conservation of the Hamiltonian, or if you want to go below the H1, you use the I method. Now, if you have a focusing situation, then how can you get something global at that level of regularity? So this is the work of Bregan. So he shows almost sure global well posing in H1/2 minus for defocusing and focusing when the mass is small. So this set here, H-1/2 minus, is in fact where the support of the invariant measure for this problem lives. And that's why you do it there. So it remains open what happens if you are above this guy. This is just a single point. It's a single, only in that space, nothing above that. So now we want to see what happens when you are above 1/2. And again, just like before, anything which is of better regularity is not seen by this invariant measure at that level. You just don't see it. So you cannot claim anything about the data that live in this sigma. It's very similar to what I did before. This is the extra piece. When alpha is 0, you go back to Bregan's argument. And I'm not going to go through the proof again because I did it before. It's very similar. The only thing that you have to remark is that the Bregan proof for the global well-posedness almost sure, it's actually more on the deterministic flavor. What I showed you before of using the independence of the random variables is actually no needed in one dimension because you already have the existing solution. But for our purposes, you actually need to show that the difference between the linear evolution and U itself, that means W, is in a better space. And that's not given by Bregan, so you have to redo the whole proof in a way. Okay, so now let me look at the third problem. So this is the one that is closer to the wave equation. So let me restate what the problem is. So it's now here, this is funny, almost surely. And that's because it's really the theorem that we can prove is that there is a set which is almost of size 1 for which you can do something. So since it's not exactly of size 1, I just call it almost. So this is local well-posedness for the 2D wave constant mean curvature equation. I will write down in the next slide what that is. In HS for S greater than 1 minus epsilon. And let me recall a little bit like a very small subset of what Igor talked about yesterday. And let me explain why this is a problem that it's interesting because it's linked to geometry and because it's very limited what we can do with the deterministic setting that we have so far. So let me, just as a reference, let's first look at this problem here. And just like Igor wrote something like this, yes, on the blackboard, this is the derivative of t square. And because this is not in one of the null form, and which I will write again next slide, we will not get the best possible results in this contest. So let me tell you what we get. So if you rescale u lambda tx, this is the rescale, then the critical exponent is n over 2. And what we have is the following. So with energy methods, local well-posedness is proved for S greater than n over 2 plus 1. If you improve a little bit over the energy method, in particular you start using streetcars, the local well-posedness is for S greater than the maximum between these two numbers, n over 2, n plus 5 over 4. And this is sharp thanks to the counterexample on limit plant. So in particular, in 2D, when we look at this problem in 2D, we have a local well-posedness for S greater than 7/4. This, as I said, and like Igor explained very well, if you replace this nonlinearity with a null form, things get much better. So let's see what happens. Now, we have two kinds of null form, one better than the other, and this is the first one, that's Q0, and then we have Q alpha beta. Also, they were mentioned yesterday as well. And the null form were introduced, as we very well know, from Sergiu, and you can use it, and he used it with Macedon to improve the regularity on which you can do the well-posedness by exploiting the cancellations that come in the null form itself. So here is a little bit of a subset of the history that Igor gave us yesterday. So in particular for the type of equation that I will mention later, so the 2D case, I would like to point out this result here. So if S is greater than 5/4 in 2D for this kind of null form, then the well-posedness is due by directly or by using the estimates of Sergiu, Klainerman, and Salberg. Okay, so let me go to, sorry, I wanted to mention also that for S strictly greater than SC, that's the critical element, there is a more recent work of Grigorian and Ahmad, but they use Fourier-Lebesgue type spaces that are not the usual Sobolev spaces, but they rescale, they are in the range in which they rescale with the right way. Okay, so now this is the equation, the wave constant mean curvature equation. Now I'm not a geometer, so if you have to ask questions about this from geometry point of view, I guess Magda is certainly a better person to talk to. But I'm going to present the analysis behind it. So the equation is box U, and then you have a UX curl Y. Now U and T at time 0 is U0, U1, and they are in HS and obviously HS minus 1. And I'm thinking of U from R2, and 1 is the time, and into R3. So everything has been embedded into R3. So from now on, we are into R3, so it's a vector solution. But also for the later, what I'll show you in a moment, I will ignore that I'm in R3, just like we saw in the previous talk. We just concentrate in one of the vector components. So it's not important the fact that we are in R3. But it's important that the target is not kept to be a manifold, it has been embedded into something. So the result for local well Poisson of this for S3 half is a consequence of Klainerman-Macedon, but you can improve that, and you have actually S greater than phi quarter. But phi quarter is greater than the H1, where the energy lives. So we would like to try to reach the H1 and see if we can do that. Okay, so let me think a little bit just like in the case of the Schrödinger. And now let me just remind you that because you have a derivative here, you just do not expect that you can use the argument of Burke and Setkov. You have to use something more sophisticated, which is more closer to what Bregan did. So I'm taking my initial data. By now you are familiar with this kind of writing here. So this is an element in H1 minus epsilon. So I'm even a little bit below H1. And one of the things that I have to estimate, just like in parallel to that piece that I estimated for you where I used the independence of G, when you look at the solution of the difference equation between the solution that you want and the evolution of the linear part, you're going to have to end up evaluating or estimating terms like this. This is the nonlinearity when the functions that you are crossing are both the evolution of the random piece. So after taking Fourier transform and writing everything in convolution and so on, this is what shows up. Very important is this term here, which expresses, in a sense, the fact that you are in a no-form condition. And the way the set S where you sum is m equals n plus k. That tells you you're doing convolution. And tau equals n plus k, which tells you that you live on the cone and you are convolving. Another important thing to remark is that these G's now are real, are not complex, they are real. And I wanted to estimate this L2. So let's proceed with that. And again, just like I did in the case of Bregan, I'm going to replace the L infinity, the absolute value of this quantity, with an L2 on omega. What does that mean? So I replace this guy with the integral on omega of this term, that's one of them, and then times the second one right there. Okay? Now, if you remember Bregan's argument, in order to use the independence, I needed to weak ordering because I needed to remove some frequencies. Here I didn't remove anything, so it looks like maybe I cannot use independence. But if you stare closely, you notice that, for example, n has to be different than k, right? Because if n were k, this term would be 0. And so that's how the null form helps. It removes a priori frequencies so then you can use the independence, and that's what you get at the end. This is has quite a lot of decay, and you can close. So one way of seeing the null form condition is exactly by in order for this coefficient to be non-zero, then the n and k is to be different, and so on. Independence make it 0 itself. So either you get 0 by independence, or you get 0 because the frequencies are the same. Okay, so this is a strong decay, and that helps in closing. Of course, this is just a tiny little piece of the argument, but I hope it gives you a little bit of a flavor. And in order to go to global, well, there is a few things that you can attempt, but certainly not the invariance of the measure, because we don't have a measure in that setting. And there are some kind, like I said, the high-low, possibly the energy method, but really doesn't work. And one last thing that I want to say is that what I showed to you now was only local well-posedness. If you want to do something global, what can you say? Well, this method allows you to say that if you give me, for example, as an interval size t, I can find a solution that covers all the way to t. And in fact, the set of the initial data that provide me those solutions which are as long as t are of a certain measure which depends on t itself. So this is a good method to claim that, for example, in supercritical situations, there are in fact global solutions, but not that many of them. And I will skip that, and happy birthday, Sergio.
Questions?
Yes,
David.
Do you have any methods for dealing with random forcing terms?
I didn't work on that, but that's so in a sense the part which is purely random when you do the difference equation, there is one piece which is purely random. You kind of forget that that's depending only on the initial data. So it is kind of behaving like a random forcing term. So, but then what you do is to be able to control that, then you take the initial data in a certain space. So, but I think of that as a forcing. Yeah.
Sergiu.
So this concerns the periodic case. Now, it's known.
Oh yeah. So this one, I forgot to say that I showed to you the periodic case because it's easy to see the frequencies and so on. But if you remember, at some point I showed how you can randomize things that live in our N by randomizing the blocks of you look at in the Fourier space, and you cut the frequency in boxes. So you go back and you randomize those pieces. And for this, it works that way as well. Yeah, thank you. I've forgotten about it.
Other questions? If not, let's thank Gigliola.
Thank you.